All right. So just a quick review on what we did last day, right? We start after we did error calculations and things, we started to look at forces, and we started to look at what would happen to a force acting at an angle to the horizontal, right? And we said that this force had two components, right? If I pull an object along this direction, it will be moving horizontally and it will be moving vertically as well. How you get the horizontal component? Real easy, right? This is the angle. This component is adjacent, right? So once you figure out the adjacent, here's F cos theta. Once you figure out the adjacent, the next is automatically sine. That's it, right? I also showed you if you have an object and you have like all these forces acting on it, you resolve vertically and you resolve horizontally. So you might get something looking like that. And then the result here. You okay with that? And I'll show you how to do it using what? You find the result down here. Maurice, what is it? If you have here and you have here, Pythagoras, right? And then we made it slightly more complicated, right? We made it slightly more complicated, where I gave you a force at an angle, and I asked you to find the result on here. What's the first step again? You have to resolve F horizontally, and you have to resolve F vertically. That's okay? So your diagram in the end will look like that. And you resolve it just like this. That's okay? And I gave you one other scenario where if you have an object here, right? The forces acting on it will be weight and contact force, right? And I told you the object will naturally slide downwards because of the component of weight acting here, parallel to the plane, and this contact force is equal to the force here. Right? And I showed you how to resolve that. Okay, today we're moving on to equilibrium. Right? If I told you that this system here is in equilibrium, I'll share the notes. When I add you all to the group today, I'll share back the notes again, right? If I told you that this system here is in equilibrium, right? If I told you that this system here is in equilibrium, what does that mean? Which force is the same? Right. So all the mutually perpendicular forces are the same, right? So these two are the same, these two are the same. So basically we could say F1 equal to F2 and F3 equal to F4. Or we could say the resultant is what? Right? The resultant forces. That's okay? Yeah. So let's see if we can apply that, right? Again, it has slightly more elaborate notes on it. I just give you the things that we need, right? All the important things. All right, so let's take a look at some examples here, right? Yeah. You know, very good. All right, so let's take a look at a few examples. Right, let's take a look at a few examples, right? Again, all the examples we assume if the system is in equilibrium, right? Right, if the system is in equilibrium, let's take a look at this here. These you can do mentally. Here's 4 newtons. What is x? Right, x is 4 newtons. What about if it's something like this? X is what? 10 newtons, right? What about this? What about this here? What's x and y? Right? Right? Because it's in equilibrium, these two here equal, these two equal. That's okay? Suppose I make it a little more complicated, Marcus. What's x? Suppose I make the system a little more complicated there. It's in equilibrium, right? What is x? What is x? Then again, it goes there.
So that's separated, right?
Right?
So it is separated. X and Y out.
I mean, resolve this. Oh, okay. So you say to resolve this, find the vertical component and the
And since in equilibrium, the component will be 3 newtons. Right?
since it's in equilibrium, the vertical component will be
4 newtons, sorry,
and the
horizontal.
okay. That can pass. Why is still thinking?
So I'm saying, right.
Oh, you got it. Yeah. So what Nathaniel? So what Nathaniel did is he found the resultant here. Right? He found the resultant of these two instead. Because remember, I didn't give you any angles or anything. Right? But that's a good option as well, right? we could make up and say here theta, right? But what Nathaniel did is that Nathaniel said that the resultant of the 4 and the 3 is 5 newtons. He used Pythagoras theorem, right? And he said that that 5 newton is the same as x. So x is 5 newton. We can work out the resultant here. What's the resultant of these two? Right? So that'll be a force acting here, right? So everything equilibrium, and these two have to be equal. Why? Go ahead, why?
I didn't see it in the angle now.
I know, so because I didn't give the angle, you can find the resultant here, which will be equal to this. So think about it, right? If I have this object here, and I apply these two forces to it, right? It will move along this direction with the 5 newton force, right? So if I wanted to get it in equilibrium now, right? So if I want to get into equilibrium, I apply a force opposite in direction, equal in magnitude. That's okay? So that was a nice short way to work it out. But I like your way too, right?
I like my way.
Okay, I like your way more. That was real good, Daniel. All right, online. So the method I would have liked was for this particular example, I wanted the resultant here, which was 5 newton. Therefore, x is equal to 5 newton. Now we're going to Marquis method, right? Online, are you okay? Yeah. Let's go to Marquis method. This time, I'm using the same thing, right? I'm going to find call it f, but this time allowing here to be theta, right? And I'm going to use Marquis method, and I'm going to get f and theta. And copy it up, and we're going to do 5 together. But F already. I'll say almost all these things in the handle. The question to be different. Okay. So what I wanted to do is use the book to write everything question. So you have more practice, right? So you have more examples. Is it good? Yeah, like the one I gave you here. You're gonna resolve, we're gonna do it in that method. All right. So we're going to get the two components. I'll give it this, right? We're going to get the vertical component acting downwards, and we're going to get the horizontal component acting to the left. These two are the components for this. You see that? Right? Please help me resolve this now. What will this be? Cos or sine? The angle is here. Cos. Cos, so that will be f cos theta. If one is cos, the next is sine. Right? And we know that since in equilibrium, what we know? Since in equilibrium, we know here equal to here, correct? So we know that f cos theta is equal, actually, I want to put the next one on top for a reason, right? So I'm doing horizontally first, right? So I'm going to resolve horizontally first. So I'll get f sine theta. F sine theta is equal to 3. And f cos theta is equal to 4. That's okay? I need some help here. How to solve this? Huh? Fine, it's an f from theta. What we can do? Two unknowns, right? So we're supposed to solve simultaneously, right? But what's an easy way to solve this? Anybody seen it? There's a reasonable sign on top on cos on top. Oh. So that. So I can divide here and I can divide here. That's okay? The f will cancel, and I will get tan theta is equal to 3/4. Very easy and fit. So theta is equal to tan inverse 3/4. Do I shut one master? Do I? Right here. Did that master? Did like master? How much is it? What's this here? What's tan inverse 3/4? 36.87. Alright, online, are you okay there? And then I want you to solve f, right? F is equal to 3/3 sine theta, which is 36.87. How much is that? How much is 3/sine 36.87? How much, Jacob? Without even working it out. With your head real fast. Head up in your head? It's supposed to be what? What is it supposed to be? 5, right? 5. How much you got? Alright, John, we got it wrong though. 4 points. What you can do, right? If you want to get the exact value, put sine, open bracket, tan inverse, and you'll get the exact value. All right? What's the first time again? I just remember it first. The law. Now your next use. Yeah, more so right now, right? Wait, forget. Online, are you okay? Online, you're okay? All right, nice. Oh, wait, sorry, level 2, so,
I don't think it makes sense.
all right, so that's the way you work out questions like this, right? Let's try one more now. Yeah. Oh my God. I make subject here. Sure, what time? Right. Oh, yes, you're coming on, right?
Yeah.
You're on, right? Right, number 5. Let's just try one more here.
Number 6. Number 6.
Sorry. Find f and theta, please. Find f and theta. Right. Theta. Yeah, when you find a new bar result on here. Alright, let's check it out. Oh, sorry. Right, first thing first, I just want to simplify my diagram a little bit, right? So I want to see the 6 on this one. I want to resolve horizontally one time. Right? 6 and 1 means the resultant is 5 to the left. Right? I go down result F. Here will be cos. Here will be sine. Right? Because we're moving upwards and to the right. I no longer have to write this. I no longer have to write this. I just have to write it. Well, and that's it. That would be F sine theta is equal to 5. F cos theta is equal to 12. Yeah. Right, finish it up fast, find F and theta. Right, find theta and F, right? And what's that? What do you get that? I don't know. I can see F is equal to 4. Alright, so let's see what you get here. Alright, so I'll get here. So if I divide 1 and 2, we get tan theta. Tan theta is 5 on 12. Yeah. Right? So when you solve theta is how much? 22.62. Right? And then F will be equal to, make F the subject here. F will be equal to 5 over sine theta. Right? If you do want to round up here, what you can do, right? You could write 5 over sine, and instead of writing 22.62, you could write tan inverse of 5 on 12. Right? So that way you do have to round up, right? Or you can just write that in. And if you do it exact, you should get 13. So get this one here, those who knew you might can get this one out, or if you're listening before you should. Right? Here's one. I want to keep this block. I want to keep this block in equilibrium. I want to keep it stationary. So my question is to find the direction and magnitude of the force to keep this block stationary. Right? We draw the diagram, and I want you to write underneath, find the magnitude and direction of the force to keep this block stationary. Find the magnitude and direction of the force to keep the block stationary. Right? So we're going to do applied mass. There's unit 2 applied. So I don't know like it from now, right? There's unit 2 applied. Right, I'm done. There's unit 2 applied. Right, take your time. I want to know the force P that will keep this object in equilibrium. I gave it the mass and I gave it gravity. Right? Look back at how to resolve, right? Right again, Coleman. What direction will you, if I have no force acting, what direction will this move in? It will come down like that, right? Parallel to the plane, right? So what direction has the force has to act in? Opposite, right? So the force have to act this way. Let's call it P. How that helpful? I don't know if it's helpful.
Really was after.
Because the P will be mutually equivalent to the force acting.
Mutually now. Very close to it. Very close to it. So think of how you're gonna find. Guys, what y'all came up with?
So I hear basketball, thank you, young guy.
Alright, so first thing first, right? You should at least have the force acting on the object.
Yeah.
What's the force acting on the object? Right, the weight, right? The weight is the force, right? So that will be 5 by 9.8, which is how much? What's that? 49. So that's 49 newtons, right? Katrina, anybody online figured it out? There is something that we have to do. So P has to be equal to the force that'll pull it down, right?
Yeah.
What is the force that'll pull it down? What is the force that'll pull it down there? I'll show you this last week. Not right. The component of weight. The component of weight acting parallel to the plane, which is 49 sine 30. That's okay. Remember, I showed you last week that this 49 newtons has a component parallel to the plane, right? That component parallel to the plane is equal to, right, P. And the one perpendicular to the plane equal to R. Right? But I don't really need R. I don't really need R right now, right? I don't need R right now. Right, so your answer is P is equal to 49 sine 30. I didn't ask R, but I just write it anyway. R is 49 cos 30. Right? So this one, 49 on 2 newtons. This one is 49 root 3 on 2 newton. That's okay? But this is the force that will keep that in equilibrium. Are you okay with that? Wait, bye-bye. Well, it's just a bit so copied. But you follow up on here, right? These two forces equal, right? Of course, I can make it a little harder by putting a next force here. Now that's more applied. Nice job, Yash. Yeah, that's good. Huh? If you message the answer, yes, for yourself. All right. I just want to complicate this scenario a little bit again. What will happen with this object? This object will, as the object slides, right? Based on the surface. What do I have to consider? Friction, right? So I have to consider friction, right? And Darian, what do you think this contributes to friction? What do you think contributes to friction? Look at the diagram on the board. Yeah. What do you think contributes to the friction? But what contributes to the friction? Well, the weight, okay, weight, and what else?
So this will be study around object side.
Right, but something that I'm looking for. See? See what? Well, the mass contributes to the weight, right? Right, so the weight contributes to the weight, the weight contributes to the friction, and one more thing.
See, that there's no friction, that's surface.
Okay, so something else, something else. The hints? Nah, I don't know hints again. Right? Right? What would have happened? Would the object have friction if it wasn't touching? If it wasn't touching the surface, it would have had no friction, right? But because it's in contact, it has, right? Because it's in contact, it has friction. So therefore, R contributes to the friction. That's okay, the contact force, right? The larger R is, the greater the friction. And what contributes to R?
Wait. The larger R is the greater the friction.
Yeah.
Because friction of the
Think about this. The larger the contact, the larger the contact with the surface, the greater your friction value.
Yeah.
Right? And R comes from here. A component of it, right? You're saying that? So yes, part of the answer is right weight, right? Right? But the more, what do you word? The more accurate, right? The more accurate response is R. Okay? R contributes largely to the friction, right? So I just going through that small note in the handout. And then let's take a look at friction, right? Elijah, you okay? Elijah. Yeah. Only just one class we'll miss this month, right? That idea. Right, the answer to one, right?
Yes.
Oh, okay, yeah, that'll be next one. Yeah, that'll be next. No, it's Friday. Friday, I will be here, right? Yeah, so that we first kind of plan. But next week Friday, is class like normal, although it's right? Class like normal.
Yeah.
Alright, so you have all these types of forces. Well, it's in your handout, you don't have to write this, right? Contact forces are produced by physical interact. Oh, sorry. Anybody know how to fix this? I don't know how to get back this pulse. No, it's the one full screen right here. Oh, I said. I don't know. Anyway, contact forces are produced by physical interaction between bodies. Applied forces, pushing and pulling. Force exerted by one object on the other. Frictional forces. That's the force which tends to oppose the relative motion between objects or surfaces. Tension force. So the reason I'm showing you all these is that if I give you a scenario, you have to be able to draw all the forces acting on the object. All right. Tension force. The force acting on a spring or wire. Or a spring which is held taut, right? That should be TAUT, right? The normal force is a force exerted on an object which is resting on a surface or a fixed support and are normal to the surface, and you have non-contact electric forces and so on, right? Then one I want to focus on, I want to focus on frictional forces. Actually, before I do that, and this example here, some all the forces acting place. That's the wall. That's a pendulum. What are all the forces acting here? Tension acting towards the
Fixed point.
right, towards the fixed point there. What else? Weight, nice. All right. So make sure you can put all the forces active, right? After play there in the office. Right? What about here? This question came a lot, right? Let's say I gave you a wall, and on the wall I have a plank. And the plank leaning on the wall, right? What are the forces acting there? Take your time. You should have at least how much? 4. In fact, let's make it more complicated, Jacob. The surface underneath is a rough surface. That's a rough surface there, right? What are the forces acting? Right? Acting where? The wall is smooth, but the ground is rough. So you have friction acting on the ground in what direction? To the left or right? To the left, nice. So you have friction here. What of course? Right, you only remember gravity, right? Weight, right? Gravity is not force, right?
Yeah.
So the next one is weight, right? What else? 2 other forces missing. Any friction on the wall? The wall smooth, right? Contact forces here. And contact always acts perpendicular to the surface, right? Where do I put the next to contact force? Right? One perpendicular to the wall and one perpendicular to the right. Let's call this R1 and let's call that R2. All right. So those are the 4 forces active. You okay with that? Everybody online? All okay with that? What did Katrina answer? Kaylin, are you okay? Kaylin, you listening? Viraj. Alright, so those are all the forces acting and make sure you can draw those in fact in my favor. Add that in. I can, I know what I'm putting that, I'll do it. Add that in, please, just draw that in, please. Draw the forces acting in those two scenarios, A and B. Draw the forces acting in those two scenarios. Right, always remember that in normal reaction acts 90 degrees to the point of contact, right?
Directly the same.
Ready? Ready? Alright, one quick thing on frictional forces, right, frictional forces. Right, if the force that opposes or tends to oppose the relative motion between two bodies is called the force of friction, right? Frictional forces are present in the relative motion between two solids in a liquid and gases and the solid objects moving through liquids and gases, right? So you have friction, all those things, right? It's in the handout. Right? Whenever there is relative motion between bodies, work is done against friction, and the work done is converted into thermal energy. All right, all those things you know already, right? Right, there's just one thing I want to point out here. Frictional forces in solids, right? Consider an object of weight W resting on a rough horizontal surface, right? But what's the keyword there, Daria? What's the keyword there?
It's.
Daria, pay attention, boy. Rough, right? Rough, right? Right. So there's something I want you to pay attention to, right? So consider an object of weight W resting on a horizontal force. A gradually increasing force is applied to the object parallel to the surface, right? So what you're doing, those are all the forces acting, right? But I have a question, right? So imagine you have that object there. You have that object there, right? And you're applying a force. Will any force move the object? Will any force move the object? No. Right? Anybody can say what the force has to be larger than? To move this object here. Right? To move that object there, right? You have to apply a particular force in order for it to move in that direction. You can't apply any force. It has to be a particular force. But anybody can tell me any specific about that force?
A force that's greater than R.
A force that is greater than R, you're real close to it. R acting vertically.
A force that's greater than
F, right? Has to be greater than F. That's okay? Right? So here's what happened. Initially, what's the diagram here? Yeah, F is the frictional force, right? What's your there? Initially, as P is increased, the object does not move and is therefore in equilibrium. So F is equal to P. That makes sense?
Yes.
Sure, Gavin, that makes sense? So initially it's in equilibrium, right? But if the object remains in equilibrium as P increases, so you're increasing the force P, then the frictional forces also increases. At a particular value of P, the object just starts to move, right? The object just starts to move. At this point, the frictional force is a maximum and it's called limiting frictional force, right? The frictional force will not go beyond that value, right? And the object is said to be in limiting equilibrium. The frictional force which acts while the object is still stationary is called static friction. And when the object is in limiting equilibrium, F is proportional to R, and have a little mistake here. F is equal to mu R. Okay, so at limiting equilibrium, F is equal to mu R. Remember I told you all that friction is dependent on the contact force, right? Larger the contact force, the larger the friction. Okay, so at limiting equilibrium, F is equal to mu R, and mu is called the coefficients of friction. Every surface has its own coefficients, right? So if I change the surface, then that mu value will also change. Yeah, when you have this happen, I'll send it back again because I know we're gonna add two of them, right? But this only handout here. That's okay. So that's something I wanted to point out when we're looking at this scenario here. Are you okay with that? So let's just do one small question on limiting equilibrium. All right. So head up limiting equilibrium. One small question on this. Right. This never really came before, but it's on the syllabus and it could come, right? Yeah. All right. So I want to give you one small example on that. And again, it's going to build on this. Right? It's going to build on this. All right, so I just want to do one small example, right? Right, the coefficient of friction is 0.3, right, Marcus?
Yeah, tree.
The coefficient 0.3, right? The coefficient of friction is 0.3, right? So this object is not moving, it's at limiting equilibrium. Right? So if this system here is in equilibrium, I want you to find three things for me. Find R, find the friction, FR, and then find the force P to keep it in equilibrium. Very similar to what we just did. Right? So I've given you a scenario here. It has friction acting. Well, it's in limiting equilibrium. Right? So what I want you to do is to find R for me, find the friction, and then find P. I just remind you that friction is equal to what again, P? Friction is what? What's the formula for friction? Mu R, okay. Actually paying attention, man. Mu R. All right, so I have a small question here for you. Find R for me, very similar to that system there because it's in equilibrium. Find friction and then find P.
Yeah. Pada pasti malah saya dulu nunggu kita.
Say that I'm going to watch. Never said a thing.
What time is finished?
It's that one.
Huh?
That one. The only consensus. You will think about sit up. Or not. What was it? Was the last one.
Right, the building's like it's crazy.
Right. Yeah, yeah, correct. I get myself. Don't let it. We thought that. No, but.
Hurry up, please. Hurry up. You've done, right? You've done, right? Careful with feet.
Yeah.
Alright? Right, so remember, anytime they have to define friction, friction is mu by R, right?
Yeah.
Right? And they give you mu. So how we get R? First thing we have to do is we have to resolve. Right, so we have to resolve this, of course, because R acting here. When I resolve here, that'll be 10. Remember, R is perpendicular to this. This is acting vertically downwards, right? So these two should not be in the same direction. R is this, and then when I resolve this vertically downwards, I'll get 10 sine 30. All right. So R is what? R is equal to 10 cos 30, which is 5 root 3. That's okay? 5 root 3. We're actually getting through. I just would like to know. Right? How we getting friction? All right, Darian, friction is what? Which is 0.3 times. Well, I would just, what is that? Right, P is what? How you get on?
Because you had to find 10, 9, 50, and then 5, 50. I mean, it's fine, what? Because he will be 10 side I mean, it's the opposite.
So we have a slight problem here. Here had no friction, so P was equal to that. But here, it's in equilibrium. These two equal to that. No. Right online? So you have to consider the friction now. So you're going to say that P plus friction, P plus friction is this. P is equal to 5 minus. Why am I minusing it? Why? Because, right? Because for this to be in equilibrium, the two forces acting upwards have to be equal to the one force acting down. Right? So this plus this is this. So to find P, at the minus friction. That's okay? So you have to consider all the forces acting, right? Alright, online, are you okay with that? So we add on one more little thing, right? Karina. Kiran, are you okay? Kiran, you follow the point on that? Kiran, see Kiran listening, Kiran message. Right, Kiran message, so it might be different. Yeah. Are you okay with us? Right? So it's important, watch here. It's important that you understand for object to be in equilibrium, again, all the mutually and perpendicular forces equal. These two equal, these equal. Okay? These are perpendicular to this. Are you okay with that? Right? I'm not going to do it, but I can make this system more complicated by instead of P acting parallel, Marquis, instead of P acting parallel, I can let P act like this. Right? So if P acts like that, you have to resolve it. Right?
Oh, yeah. So you like straight, that's true, and tell me how that perpendicular.
This horizontal, this, right? These two parallel, horizontal. Right? So if I put P here, in order to work this one out, I have to resolve P parallel and perpendicular.
So how about we just leave P on the other side?
No, I'm just saying you could also do it like that. But as I said, that is more applied, right? But that's not really fun. That's applied. Right? Question. Right? I have a question, right? Conditions for equilibrium, right? All the mutually perpendicular equal, right? But what's the next condition for equilibrium? Well, same thing, left equal to right, equal to down.
Right.
Something else.
Clockwise movements.
Principal and moments. Right? Principal and moments, right? Clockwise equals to anti-clockwise, right? So let's take a look at a few examples. Yeah, but what would you whatever. What? Line up. Yeah. For the for the path from the glory. All right, all right. Right. So the next condition for equilibrium. So these are the two conditions for equilibrium. We did one already. The resultant force in any two mutually perpendicular directions is zero. And number two, the resultant torque about any axis is zero, right? Right? All I mean by torque is that, sorry. All I mean by torque basically is the resultant moment about any axis is zero. All right? So we're gonna take a quick look at applying the principle of moments. Sum of anti-clockwise moments is equal to the sum of clockwise moments, right?
Class.
Finish.
This, what we will do now.
Yeah.
So is it an extended class?
Right? How you find movement, Marquis? Marquis? How you find movement?
The sum of all CM.
What? How you finding movement of a force?
Force.
Force by perpendicular distance, right? So that's force by perpendicular distance from paper. That's okay? Clockwise equals to anti-clockwise and right, so let's make a note of that because some of you all don't remember that, right? Right, just head up movements. Write down how to find a movement and write principle of moments. Moment is a force by the perpendicular distance of pivot. And the principle of moments P is clockwise equal to anti-clockwise about the same pivot, right? perpendicular distance.
Good.
Yeah.
Number one, how about I do like.
Yeah. But you know, right now, you just write in the part in the red. Ready? Right, that's one small thing I want to show you, and we're gonna work out on, right? So remember, once you see a system in equilibrium, right, you have to remember, two things can be applied, right? Clockwise equals to anti-clockwise, or left equal to right, up equal to down, right? Any two mutually perpendicular, result on this. All right, so let's just take a look at this, and then we wrap up, right? Watch this question here. All right. Let's take a look at this scenario here, right? Right, they were nice to you in this particular year to give you all the forces active. You see that? They give you all the forces active. They all make sense? Marquis, they all make sense? What is F there, Marquis? F is what? Well, you say it makes sense. F is what? Think about it. We just did that. F is friction, right? R and P are what is? R and P are contact forces. Right? So you have to find all those things there. Right? So that system in equilibrium, right, Faith? How we can easily find R, Faith? If we answer this quickly, we will wrap up right here.
So, if anyone. If any first.
How we find it?
I see it, so.
Yeah, Faith. Faith chance to find it. How we getting R, Faith? Remember the system in equilibrium, right? Why wasn't paying attention, Faith? I did. We have somebody online.
Yeah.
Put that. Yash. Now we have Yash. Yash, what do you think? How we getting R? Remember the system in equilibrium, right? So if it's in equilibrium, parallel, mutually perpendicular forces resultant in zero or clockwise equals to anti-clockwise. So we have to use one of those rules here, right? What do you think here, Yash? Yeah, sit there.
So.
Just what's the diagram, the answer, any diagram. How we getting R? It's an equilibrium, right? Jacob? While you're thinking then, Jacob. Downward equal to upward, excellent. Right, very good. Find the opposite R. Right, so upward equal to downward. So R is 200. That's all.
That's not.
That's enough.
That's four.
Javin, how we getting the magnitude of the normal force P? How we getting that? We just take out R, right? How we getting that? So what do you think about that, right? Here's all the homework. Right, Katrina, do me a favor now, just screenshot this. Screenshot it and send it in the group now, please. So. Yeah. Give me a hand. I got numbers on, right? So that's it, huh? Yeah. Send me a WhatsApp now. Alright, so the homework, I want you to try out this, right? It incorporates everything we did today in class. Alright? 7230529. So next day we'll continue from right here. Okay.